The National Electrical Code, specifically in the 2008 edition, underwent revisions that impact the acceptability of grounded B-phase services. Prior to this, sections 250.21.2 and 250.21.3 prohibited the use of grounded B-phase services for premises wiring systems. However, the 2008 NEC deleted these sections. This deletion was motivated by the continued prevalence of grounded B-phase services in industrial settings. The code-making panel determined that there was no overriding technical justification to prevent their use in other occupancy types as long as grounding requirements are met. Despite this change, section 250.26 remains relevant. This section stipulates that the grounded conductor must be connected to the neutral point of a Y system or to the midpoint of a grounded B-phase circuit. Therefore, when replacing a grounded B-phase service with a Y service, ensuring proper grounding of the new service is crucial for safety and code compliance. The rationale behind grounding is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers and fuses, thereby minimizing the risk of electrical shock and fire. In a Y system, the neutral point is the common connection of the three phases, providing a stable reference point for grounding. In a grounded B-phase system, the midpoint of the B-phase winding serves as the reference point. When transitioning from a grounded B-phase system to a Y system, it is essential to verify that the grounding electrode conductor is properly sized and connected to the neutral point of the Y transformer. Furthermore, the equipment grounding conductors throughout the premises wiring system must be securely connected to the grounding electrode system. These conductors provide a path for fault current from equipment enclosures and other metallic parts to the ground, ensuring that these parts do not become energized during a fault condition. The size of the grounding electrode conductor is determined by section 250.66 of the National Electrical Code, and is based on the size of the service entrance conductors. The equipment grounding conductors are sized according to section 250.122, based on the rating of the overcurrent protective device protecting the circuit. In addition to grounding, bonding is another critical aspect of electrical safety. Bonding involves connecting all non-current carrying metallic parts of the electrical system together to create a continuous low impedance path. This includes metal conduits, metal enclosures, and metal water pipes. Bonding ensures that all these parts are at the same potential, minimizing the risk of voltage differences that could lead to electrical shock. The bonding requirements are specified in sections 250.90 through 250.102 of the National Electrical Code. The main bonding jumper, which connects the equipment grounding conductor to the grounded conductor at the service equipment, is particularly important. This jumper provides the primary path for fault current to return to the source. The size of the main bonding jumper is determined by section 250.28 and is based on the size of the service entrance conductors. When evaluating an existing electrical system, it is important to consider the age and condition of the equipment. Over time, electrical equipment can deteriorate due to factors such as corrosion, vibration, and thermal cycling. This deterioration can lead to reduced performance and increased risk of failure. A thorough inspection of the electrical system should be conducted to identify any signs of deterioration, such as cracked insulation, loose connections, and corroded components. Any damaged or worn-out equipment should be replaced with new equipment that meets current code requirements. In a specific scenario of redeveloping a building from a medical occupancy to bank offices, it is crucial to assess the existing electrical system to determine its suitability for the new occupancy. The electrical loads of a bank office are likely to be different from those of a medical facility, particularly with the elimination of the large X-ray load. A load calculation should be performed to determine the total electrical demand of the new occupancy. This calculation should take into account the lighting, receptacles, HVAC equipment, and other electrical loads. The service equipment should be sized to accommodate the calculated load, with sufficient capacity for future expansion. If the existing service equipment is not adequate, it may need to be upgraded. In addition to the service equipment, the branch circuits and feeders throughout the building may also need to be modified to accommodate the new loads. The wiring should be inspected to ensure that it is in good condition and meets current code requirements. Any undersized or overloaded circuit should be upgraded. The overcurrent protective devices should be properly sized to protect the circuits and equipment. Furthermore, the lighting system should be evaluated to ensure that it provides adequate illumination for the bank offices. The lighting levels should comply with the recommendations of the Illuminating Engineering Society (WISE). The lighting system should also be energy efficient to minimize operating costs. The use of LED lighting is becoming increasingly popular due to its high efficiency and long lifespan. The receptacles throughout the bank offices should be properly grounded and GFCI protected as required by the National Electrical Code. GFCI protection is required in wet locations such as bathrooms and kitchens, as well as in areas where there is a high risk of electrical shock. The HVAC system should be inspected to ensure that it is operating efficiently and safely. The electrical connections to the HVAC equipment should be checked for tightness and corrosion. The overcurrent protective devices should be properly sized to protect the HVAC equipment. In summary, the decision to retain or replace a grounded B-phase service depends on several factors, including the condition of the existing equipment, the electrical load requirements of the new occupancy, and compliance with current code requirements. While the 2008 NEC allows for the continued use of grounded B-phase services, it is important to ensure that the system is properly grounded and bonded to minimize the risk of electrical shock and fire. If there are any doubts about the safety or adequacy of the existing electrical system, it is always best to consult with a qualified electrical contractor or engineer. They can perform a thorough inspection of the system and provide recommendations for upgrades or repairs as needed. It is also important to obtain the necessary permits and inspections from the local electrical authority before making any changes to the electrical system. This will ensure that the work is performed in accordance with the applicable codes and regulations. The NEC serves as a comprehensive guide for safe electrical installations, and adhering to its requirements is essential for protecting people and property from electrical hazards. Consider the specific requirements outlined in Article 250 of the National Electrical Code, which provides detailed instructions on grounding and bonding. The purpose of grounding and bonding is to create a low impedance path for fault current, which allows overcurrent protective devices to quickly clear a fault and prevent electrical shock hazards. Grounding electrode systems are a critical component of the overall grounding system. These systems typically consist of a ground rod, ground plate, or underground metallic water pipe that is connected to the earth. The grounding electrode system provides a path for fault current to flow to the earth, which helps to stabilize the voltage of the electrical system and prevent voltage surges. Bonding is the process of connecting all non-current carrying metallic parts of the electrical system together to create a continuous low impedance path. This includes metal conduits, metal enclosures, and metal water pipes. Bonding ensures that all these parts are at the same potential, minimizing the risk of voltage differences that could lead to electrical shock. The main bonding jumper is a critical component of the bonding system. It connects the equipment grounding conductor to the grounded conductor at the service equipment. The main bonding jumper provides the primary path for fault current to return to the source. Equipment grounding conductors are used to connect the non-current carrying metallic parts of equipment to the grounding system. These conductors provide a path for fault current from equipment enclosures and other metallic parts to the ground, ensuring that these parts do not become energized during a fault condition. Ground fault circuit interrupters, GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if they detect a ground fault. Ground faults occur when current leaks from a circuit to ground, which can happen if a person comes into contact with a live wire or a faulty appliance. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Arc fault circuit interrupters, AFCIs, are devices that are designed to protect against fires caused by arc faults. Arc faults occur when electrical current jumps between two conductors, creating a high-temperature arc. These arcs can ignite flammable materials, such as wood, paper, and insulation. SIs are required in many locations, such as bedrooms and living rooms, where there is a high risk of fire. Surge protective devices, SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can damage sensitive electronic equipment. Voltage surges can be caused by lightning strikes, power outages, and other electrical disturbances. SPD are installed at the service entrance of a building to protect all the electrical equipment inside. Electrical safety is a critical concern, and it is essential to take precautions to protect yourself and others from electrical hazards. Always use caution when working with electricity, and never attempt to repair electrical equipment unless you are qualified to do so. If you are unsure about any aspect of electrical safety, consult with a qualified electrician.